in this second video of providing you with a problem-solving recipe, what I want to do is look at a pretty simple problem that would be taken from chapters 1 and 2 of your thermodynamics textbook and make it and work it out from start to finish to try to illustrate how this little recipe can work. And so it's my hope that you'll think about the recipe, thinking about adopting what works for you, what works best for you to maximize your performance in your classwork. So let's get started. Finally, we got started. I couldn't find my share button. So here we go. Second part of the problem-solving recipe. Let's review what is that recipe that I'm recommending. 4 basic steps. Read the problem in words. Draw a sketch. Always start with a sketch. Plan your work in your mind. What am I going to do? What steps will I take and in what order? And then finally, work through the solution with pencil and paper or however you're preparing a problem solution. So you want to work down the page. You're going to be sure that you have your fundamental equations that apply to the problem written down. You're going to show and explain your work, recognizing too that units are just as important as values in this class and beyond. And you're going to try to use little short phrases, even just a word here or there, explaining your work in words more than just equations. So, of course, the devil is in the details. You think, man, this little 4-step thing, anybody could figure this out. Let's just look at an example problem and work through those basic steps. So this is a representative problem that I found basically from chapter 1. So this is a real problem. So let's read the problem in words first. Air is contained in a vertical piston and cylinder assembly by a piston of mass 50 kilograms and having a face area of 0.01 square meters. The air that's contained in that piston and cylinder initially occupies a volume of 5 liters. The atmosphere exerts a pressure of 100 kPa on top of the piston. The volume of the air slowly decreases to 0.002 cubic meters as heat is rejected from it. Neglecting friction between the piston and cylinder wall, determine the work done by the air during the process. So there's the problem statement. We have read it. Once we've read it, then we're going to go back and try to look for what's wanted and what are the key words or what kind of clues does this problem give us? So let's see what we can fish out. What's desired? The work done by the air during the process. And so what should come to our mind is W out. W out in this class, the work done by the system is what we're trying to find. And a little more detail on that, but W out, that's what we're looking to find. Okay, clues. In getting this problem solved numerically, what are some clues? Air contained in a vertical piston and cylinder. Man, that's a giveaway, right, of it being a closed system compared to an open system. And as the class goes on, you're going to be faced with having to make tougher decisions on that. But this one clearly discloses closed system. The volume change is given, but notice how here, little tricky, the units are different. Look, initial volume, 5 liters, final volume, 0.002 cubic meters. We're going to have to be careful with that, aren't we? Let's see. Details about the piston weight are given, but it doesn't give the piston weight. It only gives the piston mass. So looking ahead, we realize we're going to take the given mass and we're going to transform that into the weight of the piston. Okay. We continue to read, and it says, here's a key word, slowly. The volume of the air slowly decreases. Another key word, neglecting friction. And so in your class lectures, you're picking up that the combination of slowly and no friction, what that does is it discloses that this process would be considered a quasi-equilibrium process, one in which at all points between the beginning and ending state, the air in the piston and cylinder is always in a state of equilibrium. Okay, we're just about there, but the observant student will say, wait a minute, I'm looking for the acceleration due to gravity. I need to calculate the weight of the piston, and I'm not given the acceleration due to gravity. Oh, I'm going to have to point that out to the instructor, how dumb the instructor is for not including G in the given information. I'll get that instructor straightened out. Not a good idea, right? So because really, you're also recognizing, well, this problem is associated with doing work on the earth, right? So the piston and cylinder somewhere on the earth. And so as an engineer, you're sharp enough to know, wait a minute, look, I'm not going to lose any points for recognizing that G pretty much everywhere on the earth is 9.8 meters per second squared. So in my sketch or somewhere in my problem solution, I'm going to use G of 9.8 meters per second squared. And I'm not going to go through that exercise of trying to embarrass the instructor, right? So I think that would be smart. This would be just an example of, as an engineer, filling in some blanks maybe of some things that aren't included in the problem statement. Okay, so here we go. So we have read the problem again carefully, filled in some blanks. Next step, what's step 2? Start with a sketch. Okay, so here's our sketch. In my sketch, I'm always looking for partial credit when I'm showing my solutions. First thing I do is write down the words closed system. That's going to get me something on partial credit. I'm going to show the piston and cylinder. I'm going to show the air as a closed system. And this little dash line, that indicates that the air is the closed system. The piston and cylinder mechanism assembly, that's not the system. It's the air inside the piston and cylinder that is the system. That's why I showed that dashed line. I've shown state 1 and state 2 here on my sketch because in the problem statement it said the volume decreases. So that's why I knew the piston's going down. I wrote down given information, piston area is 0.01 square meters. Okay. I didn't really bother to write down the initial and final volume. I'll get to that. I could write it down. I didn't write it down. Shame on me, but I'll get to that in my solution, won't I? But also I drew sort of another sketch, didn't I? Because I've got to determine what the pressure of the air is in here in order to get to the work for this quasi-equilibrium process. So I drew sort of another sketch of a free body diagram of the piston, free body diagram of the piston. And I studied it and read the problem. I've got 2 downward forces pushing on the piston, the atmospheric pressure force and the weight of the piston. Let me move there it is. The weight of the piston is mg. And then the upward force, there's only one upward force, pressure of the air times the area of the piston. And I wrote down the downward forces stay constant. I can't see any reason why these downward forces would vary. They're all constants, okay? So therefore, common sense, and in my statics class that I've already taken, says the sum of the forces in the y has to be equal to 0. So I wrote that on my sketch, okay? So the sum of the forces in the upward force has to exactly balance the downward forces, and that shows me how I can solve for P of the air. Maybe I'm getting ahead of I'm planning my work, right? But anyway, there's my sketch. Okay. And your sketch does not need to be a work of art like this is. I've taken the time to create a pretty sketch for PowerPoint. Yours can be hand-drawn, and it has to be neat enough so other people can read it, but it does not have to be a work of art. Okay, next part of the recipe. Let's plan our work. Okay, plan what you'll do. Okay, it's a closed system. Okay, I got that. The process is quasi-equilibrium. I read enough of the problem to get quasi-equilibrium process. What's the combination of closed system and quasi-equilibrium? Oh yeah, that's right. The textbook reading, the workout, that's what I'm looking to find for a closed system and quasi-equilibrium process. The workout is the integral from state 1 to state 2 of PdV. Okay, got it. That's my governing equation. My sketch shows that P1 equals P2 equals P of the air. It's constant. So I need to, okay, I've got to figure out what is P of the air. Okay, got it. I think my sketch has got me on a good track to get P of the air. Okay, I'll find the weight of the piston. So I'll determine all the downward forces. Let's see. So the weight of the piston is downward. P of the atmosphere times A of the piston is the second downward force. Okay. And let's see, solve for the air pressure. Now, I think this is a typo. P of the air doesn't equal, whoa, wait a minute. No, that's correct. P of the air doesn't equal P1, P2. So this is, on my PowerPoint, this is incorrect. So just be aware of that. That is a mistake on my PowerPoint. So also, it looks like I've got another mistake, doesn't it? Do the integral to show that W out equals not P of the air times V2 minus V1. That is not correct. W out equals P1 or P2 times V2 minus P1. So that's incorrect, all right? So shame on me for not checking my work. Numerically, what's W out going to be? Do you see that, well, pardon my blunder, but we're going to get a pressure here, a pressure positive number times V2 minus P1. Do you see that that's going to be a negative value? So in our planning, and we get our numerical result, we better see that W out's going to be a negative number, okay? It's going to be easy to determine V2 minus V1, but we've got to watch out for the units because when we read the problem, the units were not consistent. We'll get the units consistent and get it right. We'll do the math, keep units straight, and then I hope that we fix this blunder in our solution. So please excuse me for that. All right, well, let's go ahead. I need another sketch, don't I? Because to depict, I need another sketch beyond what I've already drawn because I need to depict the work out so that I can visualize my solution better. Okay. And again, look at this. I've written this incorrectly again. P of air, that is not correct. It would be correct to label P1 equals P2. That's what I should label here. Okay. Here's my governing equation. W out is the integral from 1 to 2 of PdV. What have I shown on my sketch? Here's state 1 at V1, 5 liters. Here's state 2, a lower number, V2 is 0.002 cubic meters. I got to fix these units, okay? But what's the power of showing this sketch? The power is saying, I realize I've got to integrate. Now I've got a visualization of the integral. I'm integrating right to left. So the numerical result of the integral is the area under the curve. That's a rectangle. P1 equals P2, okay? But the numerical result is going to be a negative number. Watch volume units. Okay, so I've added a sketch. I've got a third sketch now. Okay, last step in the recipe. Let's work through the solution. Okay. As a practicing engineer, I ended up doing all of my computations in Excel. I created problem solutions in Excel. So you're going to have to live with me not being handwritten, but working through my solutions in Excel. All right, so I wrote down, how do I get the weight of the piston? The weight of the piston is mg. I wrote down, here's a yellow cell. When I turn a cell yellow in Excel, that means I'm fat fingering in a number. That's how I remind myself I'm fat fingering in. But notice how I do more than just put 50. I say 50, that's the mass of the piston, M sub P, piston, okay? 9.8, I didn't just plop down 9.8, I wrote down G in meters per second squared. Look, I'm including my units, and I've said that's a typical constant when G is not specified in the problem statement. So now I do the math. Mg is 490 There's the weight of the piston. And I look at my units. I've written out newtons or N. 1 Newton, 1 N is a Newton. And that's a Newton is a kilogram meter per second squared. I can sort of visually look at my work to see my units are good. The weight of the piston, 490 newtons. Okay. Now I go back to my sketch. The sum of the forces in the Y is 0. P of the air times A of the piston. That is P of the air. Okay, that's the air inside. That's the air inside the piston. That's P1 equals P2. Okay, that's the upward force. Down to downward forces. Now, P atmospheric. That's not P of the air. That's atmospheric pressure. Looks like I'm back on track. P of the atmosphere times A of the piston, and the other downward force is minus W of the piston, which I've already gotten. Okay, so now I can solve for P of the air, which is P1 and P2. Now that I'm kind of thinking live, that see, you can, your nomenclature looks like I'm using P air equals P1 equals P2. Okay, and I'm solving one equation and one unknown for P of the air. So it's P of the atmosphere plus W of the piston over A of the piston. Numerical, okay? So I'm saying determine the pressure of the air in the cylinder. So I've got W piston that I just found. I had to fat finger in the area of the piston, 0.01 square meters. Look at my units. P atmospheric in kPa, a kilopascal, that's a kilonewton per square meter. A kPa is a kilonewton per square meter. Okay. Wow. And so I'm thinking to myself, wait a minute, W piston in newtons. Look at that. P times A is kilonewtons per square meter. In my solution, I'm going to need to transform the weight of the piston in newtons into units of kilonewtons. So I didn't drag out in my work all showing, oh, I'm dividing by 1,000. I'm showing, I think it's kind of obvious, right? So I'm going to slip the decimal point of 490 3 places. So I'm dividing 490 by 1,000 to numerically get the weight of the piston in kilonewtons is 0.49 kilonewtons. Okay, so now I've got consistent units. So P of the air equals P1 equals P2 is going to be equal to, let's see, that's 100 plus whatever that turns out to be. And that's 149 kPa. Okay. So yeah, 0.49 over 0.01. There we go. So that math is right. 149 kPa is the pressure of the air contained within the piston and cylinder. I'm not there yet. That's not even the requested item. No, it didn't say solve for the pressure of the air, did it? The problem statement didn't say that. As an engineer, you just had to be smart enough to know, I need to get that in order to get the work done by the system. All right. Volume change. That's pretty easy as long as we keep our units straight. Given V2, 0.002 cubic meters. Let's stick in cubic meters as our units. V1 is 5. I needed to go in my work, and I made a little screenshot of that one page of our conversion factors to see 1 liter is 10 to the minus 3 cubic meters. Now, some people would say, I've got that memorized. I'm going to have to admit that most of my career work was not in English, in metric system. It was in English system. I needed a little refresher on that. 1 liter is 0.001 cubic meters. Okay, so I'm going to transform V1 in liters to, let's see, 1 liter is 0.001. So I've got 0.001 times 5, or 0.005 cubic meters is V1. And so now math is simple. V2 minus V1 is negative 0.003 cubic meters. We're working down the page. So you see electronically here, we're in PowerPoint. I'm kind of working slide by slide. I hope in your head you're seeing how one could simply work down the page like you'll be doing on your homework problems. Next, perform the integral. So when I'm solving this, I'm going to write out, before I put pencil to paper, I'm going to write down my governing equation again. Work is the integral of P dV. I've got P of the air, which is equals P1 equals P2. I just solved for it up above my upper work. I wrote it down. Oh, here's my blue cell. In my work, my little light blue cells mean I'm simply transferring a number from something I've gotten in previously up the page. So 149 from previous work, V2 minus V1, negative 0.003 cubic meters from previous work. Bang those two things together. In the integral, it's the area of a rectangle. To get the work out, the work done by the air in the piston and cylinder is negative 0.447 kilojoules. So it's kilonewton meters. Look at that, kilo, okay, Pascal, newtons per square meter times cubic meters. So that's going to be kilonewton meters or kilojoules. And so I tried in my solution, I tried to explain that. I didn't just do that in words or in my head. I tried to explain that in my solution. So we've got a result, clearly report. So I'm circling my result in a red, sort of a red box, okay? And then, and I've got a number, a numerical number. The work done by the system is negative 0.447 kilojoules. In a lot of cases, if you've got time, sometimes it pays to write a sentence. The work done by the closed system is negative 0.447 kilojoules. In other words, 0.447 kilojoules of work is done on the closed system. Okay, and so you notice here, back to a little thermo, we're talking about a problem-solving recipe, but I can't resist in thermo. We never say work in or work on. We don't say that. To maintain our sanity, we don't say work in. So that's why I'm always dealing in work out in this type of chapter 1 type problem. Okay, and so as a check, we got a negative number. Is just a reprise of our sketch. So I just took a screenshot of the sketch. Notice we're integrating right to left. That signals that we're going to get a negative number. So we're totally consistent with our sketch, with our numerical work. We're ready to turn this in. Okay. All right, so let's recap. So we worked through a pretty simple problem start to finish. We read the problem in words, but then we went back and really tried to look for key words, key phrases. What do we want? What's assigned for us to do? Then we drew a sketch. And so this drawing a sketch thing helped to clarify how we plan our work. These two are so closely intertwined. So now notice here, in our solution, we ended up with 3 sketches. We had a piston and cylinder, the assembly. We had a free body diagram, and then we had a pressure volume diagram to illustrate the work done. So we ended up with 3 sketches. We planned our work, okay, thought through in our mind. I needed to get that pressure of the air in the cylinder. I think I pointed out some blunders that I thought I had on the slide, and then the more I think about it, sort of multitasking here, I think I was okay where I was depicting piece of air. That's the pressure of the air inside the closed system, and I used PATM, pressure of the atmosphere, as the pressure of the surroundings. So I think I'm okay on that. Then we worked through the solution, and I tried to illustrate on my slides how I worked down the page, slide by slide by slide. I wrote down the fundamental equations that governed what we were needing to do. I showed and explained the work. We used units and wrote down units throughout the solution, and I tried my best to, I probably was a little wordy. I'd say that in your solution, because of your time crunch, you're incredibly busy. You're taking a bunch of different classes. You probably would choose to not use nearly as many words as I did, but you get the idea. Key phrases, a few well-chosen phrases or words throughout your solution is going to help illustrate how you're doing your work. Okay, that was a pretty easy problem, wasn't it? Now, in the next video, in the third video in this series, I've picked out a problem from chapter 3 that's going to be a little more complex, where some students getting into chapter 3 might start saying, I just don't know where to start, or I don't know how to start. And there's some good reasons for that. You should not, don't panic. But that's one of the reasons why I'm recommending this recipe, so that you do not panic, so that you've got something that you can fall back on before panicking. Because as you can imagine, I've graded an awful lot of homework and I've graded an awful lot of tests and a few quizzes, but a lot of tests and exams. And when students panic, a lot of times I see blank sheets, blank pages. And that's the kiss of death, because I can't even give partial credit for blank sheets of paper. And so I hope you get the idea of this recipe at least is getting you to put a sketch, as best you understand it, a sketch on your sheet of paper. That's going to get you something. And then hopefully that sketch will inspire you to get moving in planning your solution. What do I need to do first? What do I need to do next? What do I need to do next to drive towards that requested result? So that's what we're looking for in the third in this video series. Certainly invite you to check with that out as well.